Hello, my name is Deeplabv3 Soler, and I will now show our approach for the problem of semantic segmentation of unstructured raw environment. So first of all, I would like to thank the organizers for the data set and the opportunity to present our work. So to begin, we are a group from the Institute of Mathematics and Statistics from the University of São Paulo in Brazil. Here are team members. It's myself, Mateus, and Roberto. So the first thing we did was try to understand the data set. We have 23 classes plus a undefined class. The undefined class is used for labeling and overexposed areas of the image. So we need to decide what to do with it. We tested both ignoring or predicting an undefined class. What we find out is that predicting the undefined class yield the best results. So for every single image on the data set, we change the pixel value of the undefined class to a pixel value of 23. And now we need to develop a network to predict 24 classes instead. In here, we show the histogram for the training data set. We can see we have three underrepresented classes, which are sand, traffic sign, and animal classes. These classes could get in some problem, so we need to watch them out. Another source of problem is that the wall class is heavily underrepresented in comparison of the building and the fence class, which have some similarities. This could bias the network. This is even worse for the ground classes in the case of the sand class. So one way to improve the network is to use data augmentation. Data augmentation artificially generates more training samples by introducing some computer vision transformations. We use the image aug library, which was a handy tool to make a sequence of transformations. On this table, we show our transformation that we used, which are rotation, scale on both X and Y, translation and X and Y, and flip. We all used vertical flip because using horizontal flip would introduce the network the possibility of the sky be on bottom of the image and the ground be on top. And this would just only worsen the model. We also use gamma contrast and median blur. In here we have the input for the library. Another interesting point is that using some geometric transformation generates new pixels on the image. The standard for the library is to fill these regions with the pixel value of 0. But in our case, the pixel value of 0 would be asphalt. So we took advantage of the undefined class and used the pixel value of 23 instead. So for the network, we use a custom version of the image segmentation Keras library alongside with the Deeplabv3 plus Keras library. In this table, we compare a sequence of segmentation models and Bayes models combined. And from the table, we can see that the model with the best result is Deeplabv3 plus, and followed by UNet with a Bayes model of MobileNet. In here, we show the overlaid projection on top of the image. On the bottom, we have Deeplabv3 plus output, and on top, we have UNet. Now, we continue tinkering with the model. We noticed that using the same aspect ratio as the original image yield better results. So for our putting dimension, we took we scaled the original image to half of its original size. Another thing is that we found out that using the exception-based model trained on the cityscapes data set yield the best intersection of union score. So this is the model that we decided to use. This is our final training parameters. We use the Adam optimizer with the category cross entropy loss. We trained for 25 epochs with an steps per epoch of 2048 and a bed size of 6. With this configuration, we achieved a mean intersection over union score of 66.328 on the hidden test data set. In here, we show some good examples. We can see that the network did a good job predicting the classes, but there's still some room for improvements. As an example, we have this pole here and this person's legs. In this slide, I'm presenting the intersection of union for each class on the validation data set. We can see we have 4 complicated classes that are underrepresented on the data set. So these classes could benefit from more training samples. This is the opposite for the case of the animal class, which is the least represented, but still has a good score. In this image, we show the network failing to predict a pile of sand. We can see that the network predicted instead a combination of other ground classes: asphalt, soil, grass, and mixed objects. So this is something this is a problem of the network. So here we have the prediction of a video stream of the vehicle driving on an off-road road. In here we can see that the network is capable of predicting the path ahead. So we can say that it's possible for an autonomous vehicle to drive through this unpaved region using the network. There's still some noise, but I would say it's possible. So now it's just finally, we have another video that we accelerate a little bit, showing the same vehicle driving on a paved road. We can see that it's much simpler for the network to predict the asphalt rather than predict the other unpaved classes. Lastly, I would like to thank you all for your attention. And if you want, this is my contact information.
Perfect. Thank you, Diego. We have one question in the chat. It's from Honey and Cow. May I ask how you evaluate the score of the undefined class?
For the intersection over union, for the main intersection over union, we removed the class, but we evaluated like all other classes, as we are treating it like an extra class.
Okay. Yeah, for the competition, the undefined classes were then ignored during the mean intersection of the union evaluation. Yeah. Those pixel areas. Okay.
We just changed it back to 255 for submission.
Do you have some intuition between or for the good performance of the animal class, even though it is underrepresented?
Our hypothesis is that the animals are showing some good features for the network to predict. So the animals are really standing out from the other classes, and that's why the network was able to predict it so nicely.
Yeah, that can make sense, especially if comparing it to buildings and walls that could look very similar in the visual appearance in the camera.
It also show why the sand was so bad, because the sand and gravel can be essentially the same thing if you look at it in a way.
And for many applications, you could consider actually fusing them if you're really just interested of navigating the environment. But yeah, that wasn't done in this case. If there are any other questions coming in or raised hands, I don't see any. So thank you, Diego, for the very nice presentation.
Thank you. Thank you so much.